What if our universe, in its deepest quantum sense, was built from something truly simple, like letters in an alphabet? But instead of letters, imagine matrices, tiny tables of numbers, powerful numbers. Could these be the fundamental building blocks, the very Legos of all quantum reality? This is a profound question we now explore, a journey into the heart of matter and information. The world of the very small behaves strangely. It defies our everyday intuition. Classical physics, the physics of apples and planets, breaks down at this subatomic scale. We needed a new language. Quantum mechanics provides this framework, and at its core we find elegant mathematical tools. Among these tools, some stand out for their simplicity and for their profound implications. Meet the Pauli Matrices. Named after the brilliant physicist Wolfgang Pauli. These are not just abstract mathematical curiosities, they are essential. They help us describe the intrinsic properties of particles. Properties like spin. Without them, our understanding of the quantum world would be incomplete. So let's open that door. A landscape built perhaps from matrices. So what are these Pauli matrices? There are three of them. They are traditionally named X, Y, and Z. Think of them as fundamental operations. Actions you can perform on a quantum system, specifically on a qubit. Each matrix has a unique effect, a specific way it transforms the quantum state. They are the verbs in the quantum language. Mathematically, they are quite compact. Each Pauli matrix is a 2x2 grid of numbers. For example, the Pauli X matrix is 0, 1, 1, 0. Simple, isn't it? The Pauli Y involves imaginary numbers, 0 minus I 0. And Pauli Z 1, 0, 0 minus 1. These numbers are not arbitrary, they are precisely what's needed for quantum tasks. These matrices act as operators. In quantum mechanics, an operator is something that does something. It transforms a quantum state into another state. Imagine a qubit as a tiny sphere, the block sphere. The Pauli matrices rotate this state vector. Each matrix corresponds to a rotation. This is how qubits are manipulated. Before we build more complex systems, let's consider the simplest. In the world of quantum operations, we talk about unitary groups. Sounds complex, but the idea is about transformations. Transformations that preserve the total probability, which must always add up to 1. The simplest such group is called U1. It represents global phase changes, a rotation of the overall quantum state. It's like turning a dial that affects everything uniformly, but doesn't change the measurement outcomes. Now, alongside the Pauli matrices X, Y, and Z, there is another crucial 2x2 matrix. The identity matrix, often denoted as I. It looks like this, 1001. What does it do? Absolutely nothing to the state. Applying the identity matrix leaves the qubit unchanged. It seems trivial, doesn't it? The operation of doing nothing. Yet it's profoundly important. It's the neutral gear in our quantum machine. The identity matrix is the cornerstone of U1 in many contexts. Multiplying a state by a complex number of magnitude 1, a phase factor, is a U1 operation. The identity matrix itself is the simplest element. It means no change, it's the starting point. Section 4. Crafting reality, U2, and the single qubit. Now let's step up from U1. Let's explore the space called U2. This is the group of all possible unitary operations that can be performed on a single qubit. Think of it as the complete instruction set, everything you can possibly do to one quantum bit. This space is richer, more complex than U1. It allows for all kinds of rotations and transformations, not just a simple phase shift, but a full manipulation of the qubit's state. The remarkable thing, the three Pauli matrices, X, Y, Z, and the identity matrix, I, form a basis for this U2 space. What does that mean, a basis? It means any operation in U2, any single qubit manipulation can be constructed from a combination of these four matrices. It's like having red, green, and blue lights. By mixing them, you can create any color. Similarly, by combining I, X, Y, and Z, we create any single qubit gate. These U2 operations are the single qubit gates in a quantum computer. The Hadamard gate, for example, creates superposition. It takes a definite 0 or 1 state and transforms it into an equal mix of both. This gate can be built from Pauli matrices, phase shift gates, rotation gates, all of them. They are the workhorses of quantum algorithms, each one a specific recipe, a precise combination of our fundamental Pauli building blocks. This is the essence of single qubit control. Section 5. Expanding Horizons, the Ladder to UN. We've mastered a single qubit with U2. But the universe and quantum computers have more. What about systems with more than 2 levels, or systems with multiple qubits? This leads us to generalize, to climb higher on the unitary ladder, to groups like U3, U4, and beyond, UN. Each step up describes a larger, more complex quantum system. More states, more possibilities, more intricate behaviors. The principles remain, but the stage expands. What might these higher dimensions represent? U3 could describe a qubit, a quantum system with 3 basis states instead of 2. Think 0, 1, and 2. This requires 3 by 3 unitary matrices for its operations. U4 is particularly interesting. It can describe the operations on a system of 2 qubits each with 2 states, 0, 0, 0, 1, 10, 11. That's 4 possible combined states, so we need 4 by 4 matrices to operate on them. The dimensionality grows quickly. How do we construct operators for these larger systems? Often through a mathematical tool called the tensor product. This expansion into higher dimensional unitary groups unveils a universe of increasing complexity. Section 6. Beyond simple stacks, the magic of entanglement. So we can stack Pauli matrices using tensor products, we can build operators for 2, 3, or many qubits. This allows us to perform operations on individual qubits within a larger system, like flipping the first qubit while the second does nothing. This is important. It gives us local control. But if this were the whole story, quantum mechanics might seem almost trivial, just a scaled-up version of single qubit physics, a simple sum of its parts. But the quantum universe holds a deeper, stranger magic, a magic that goes beyond simple stacking. This magic is called entanglement. It's a connection between quantum particles, a correlation so profound it defies classical explanation. To create entanglement, we need special kinds of gates, entangling gates. The most famous is the C0 gate, controlled knot. It involves 2 qubits, a control and a target. If the control qubit is 1, it flips the target qubit, Pauli X. If the control qubit is 0, it does nothing to the target identity. This operation cannot be broken down, not into separate actions on each qubit independently. Entangling gates create non-local correlations. This interconnectedness is at the heart of quantum power. This is the key to quantum computation's potential. Section 7. Quantum realities, matrices in action. This journey, from simple Pauli matrices to complex entangling gates, isn't just a theoretical exercise, it's not just math, it has profound practical applications. These concepts are the bedrock of emerging technologies that promise to reshape our world. Quantum computing, quantum communication, quantum sensing, all rely on mastering these quantum operations. The Pauli matrices are there every step of the way, guiding our understanding and our engineering. Let's look at a few examples. Consider quantum error correction. Qubits are fragile. They are easily disturbed by noise. This can corrupt quantum computations. To protect them, we need error correction codes. How do we even detect errors? Often by using Pauli matrices. An X error, bit flip, or a Z error, phase flip, can be identified by measuring specific combinations of Pauli operators. These measurements, called stabilizers, tell us if an error occurred, and what kind of error it was. Then we can apply another Pauli operation to fix it. Simple, elegant, powerful. The same mathematical language, the same fundamental operators.